Hambini fans, and welcome to another episode of the Hambini Show. Today's episode is a special show because we have a voodoo sacrifice. We have entrants from all around the world to answer one question, a very popular question, which isn't Hambini, who's your hairdresser? Well, to be honest, every hairdresser that I've come across has been fit. Anyway, what we've got is we've got a load of bike frames, and people want to know, how strong is the carbon in there? So I thought we'd find out. So we've got some frames and we've cut them up. So let me go through the frames and some of the little intricacies associated with it. The first entrant, all the way from Timmy's Tea Room in Completeness, a Canyon Endurace CF SL. This one was donated to me. Thank you very much to the person who donated it. I think they know who they are. Anyway, this is, it's like the endurance geometry. It's got a stack of 532mm, reach of 370. It's UCI approved. And it was crash damaged, that's why it ended up here. Disc brakes and a BB86 bottom bracket. And what I've done is I've taken a chunk out of this one. The Young Pretender, all the way from Shenzhen in China, the Trifox frame X10. So this is a frame that they sent in that a lot of people thought was a Hambini special because, they'd send one to YouTubers that was the dog's bollocks. Now, again, I've taken a chunk out of there. It's $600, so this is a fraction of the price of this one. Even though this one, made by Quest Composites, is made in the same country and perhaps has the same quality. But we'll carry on with that in a minute. This one is BSA bottom bracket, disc brakes again, and you can only buy this direct. And now, people might not have been expecting this, but in the interest of the channel and sticking up a middle finger at that handsome chap, we have his child, the crap Cervelo S5 that I've had for many years, and we have given it a whole job. A fucking good reaming. So this thing is, it cost, as a complete bike, I think it was £6,000 in 2013 or 2014. It is the VWD edition, the Wanks Daily edition, and it is, piece of shit really. It's been hammered. So it's quite old, but it gives us an indication of if things have moved on. There was also another entrant into this, which was a specialised Roubaix, but unfortunately, somehow I've managed to misplace the frame, but I've got the results for it. Now, just to give you an overview of how carbon generally works, there are, strictly speaking, two types of carbon. There is high modulus and high strength. They are not mutually exclusive. You can have both together, but I'll describe what that means. High modulus means it's extremely stiff. So if you were to put load onto this frame, you would find it didn't bend very much, and that gives you the high stiffness. High strength is to do with at what point it breaks. So you can have a structure that bends a lot and then breaks, and that's high strength, or you could have a structure that bends very little, which is high modulus, but then the point of fracture, the point of disintegration, is quite low. The two tend to offset each other. You don't tend to get them together. Now, the reason why I've taken the chunks out of here is more for a practical reason, which is it's a long, straightish section. So on all three bikes, the loading through here should be the same, but you know, for practical reasons, if you're going to take a sample, take it out of there, they tend to look like dog bones. There are some, you know, easy features to distinguish between the three frames that I've got on here. So the canyon is quite a wide section that way, but comparatively quite narrow that way, because the geometry also has an effect on the stiffness. So the stiffness is a combination of geometry and material strength. Just looking here, I mean, you can see the huge difference in the thickness in that plane between the Cervelo and the Canyon. Okay, what I'm going to do now is take you inside and go through this in a little bit more detail. Right, well, it wouldn't be a Hambini video without PowerPoint, so let's begin. Now, the reason for this is purely, well, there's a lot of, I don't know, prejudgments and things about carbon frames. Now, as an example of this, if I show you this video, which is by Jasper Vekkel, I can't even say his name properly, but you can see him going through his Trifox frame. I mean, when you listen to him, his major gripe was the lack of technical support, even though the frame was $600. I'm not disputing his opinion, he's quite entitled to his opinion, but I feel as though there was a load of preconceptions in there about the quality, and so that's where this comes in. Now, if I roll the PowerPoint, this is gonna get a bit technical. So let's check the pen is working, because we're gonna need it here. Pen is working. Right, how strong is budget Chinese carbon, a $600 frame and a $3,000 bike frame? Right, first of all, the disclaimers. I'm 5. This has been seriously simplified to make it YouTube friendly. Now, there's going to be loads of people out there who say, oh, you've dumbed that down, you've done that down. Really, I have no choice, because the vast majority of people out there aren't all engineers, right? The other thing is the cycling media, so the usual tossers from the usual outlets, just read verbatim from data sheets and say frame X is 20% stiffer than it was last year. Well, if you do the compound 20%, 10 years ago to now, the frame should be 6 times stiffer, and clearly it isn't. So, you know, what's all that about? It's basically bullshit. Few thank yous. So thank you to Ian and John for donating the frames. So Specialized Roubaix Expert and the Canyon Endurace. Thank you very much to those people. I wouldn't be able to do this kind of thing without that, without those donations. But I'll come to that in another video about where the channel is going. Before I give you the results, I need to give you some basic engineering. I'll be a fool not to explain it to you, because if I just give you the numbers, you take it away and, you know, probably shoot yourself in the foot by doing it. Right, strength varies depending on whether it's compression, tension, or shear forces, or shear tension, compressive. Sorry, not shear force, compressive force, or tensile force. There are 2 fundamental principles. You can actually see there's 3 there, but to be honest, I'm 5 years old, so I got that wrong. Right. There's the strength of the material, which you're probably familiar with. So, you know, bike manufacturers usually refer to T800 carbon or T1100 or whatever it is. There's the second moment of area, which I'll cover, and the polar moment of inertia, again, which I will cover. Firstly, to try and explain the difference between compression, tension, shear, and torsion. Right, compression is you take an object and you squash it together. So here's a cup that I got, and if you compress it, yeah, it compresses in that plane, but it expands that way. Okay, so that's one of the side effects that you get. Tension is where you pull it outwards. Okay, now shear is where you have 2 surfaces and typically a glue joint in between, and then try and shear them apart. Okay, it's a shear force. And to give you some practical examples of that, breeze blocks or cinder blocks. That's, you know, an example of an item that is very good under compression, but as soon as you put it under tension, it's crap. It just crumbles. But you can stack loads of them up on top of each other because they're very good in compression. Another example is this. This is the Clifton Suspension Bridge in the city of Bristol in England. And it was designed and built by a guy called Brunel. He's quite a famous engineer. He didn't have that many people that he was shagging, and some people suggested he was gay, and in those times that really wasn't considered all that good. But we digress. That pillar here is under compressive force. This cable is in tension because it is trying to be stretched, okay? And the roadway is trying to fall apart. So what that's trying to do is basically just go straight down. So there your forces together. Another example is Velcro. Good example for shear force is Velcro, because as you stick the two things together and then try and pull them apart, that is a good example of shear. So Velcro is very good in shear forces. Right, a real world example. So this is basic engineering beam theory. So what we've got here is the beam, which has a length L. Now these things on here are mechanical symbols. So we've got point load and point load on rollers. They're to do with moments and forces, but we don't really need to cover that. What this picture below shows is as you apply a force downwards, F, smack bang in the middle, this top surface here is now in compression because it's trying to be shortened. The lower surface beneath it is in tension because it's trying to be stretched. This centre line, and centre lines are dot dash lines, is called the neutral axis. The neutral axis is where there is no tension or no compression. And this leads me on to the next thing, which is the second moment of area. The second moment of area is the resistance to bending. So the idea is to move material away from the neutral axis. You might think, well, how are you going to explain that? Well, if I get a ruler like this, if I try and bend it that way, it's quite flexible. If I turn it that way and now try and bend it, I can't bend it. And that's because the second moment of area in that plane is much higher than it is in that plane. And that's why I-beams are shaped the way they are. So an I-beam has a lot of material away from the neutral axis. So that distance there. Okay, you want to maximize that distance. If you double that distance, you will make it 8 times stiffer. Similar thing applies to twisting. So if you were to take an object, typically they are round circles, and then apply a turning force to them, the bigger that you make the diameter of it, the more resistant it becomes to turning, to twisting. An example of that would be bolts. So if you increase the bolt size, you can typically put more torque on it. And this is the mathematical equation for it, but we don't really need to cover that. And if you are interested, these are the formulas for different kinds of shapes. So you've got, well, usually in most of the world it's BD cubed over 12, but you know, this is for a rectangular section, circle, tube, square, hollow tube, and an I-beam. So that covers kind of the geometry. We're getting really a lot more technical here, but this is the a typical strength stress-strain curve for a metal. I've included it for completeness. I appreciate that most frames are carbon, and we're talking about carbon frames, but I've included it for completeness. On the left-hand side, we've got stress, which is effectively the amount of force you're applying on a face, and then strain is the amount of stretch. So if I was to take the ruler again and then stretch it really, really hard, I can't apply enough force on it, but I could probably get like 0.5 mil of travel on it before it snapped. If you follow this through and start off, you know, at the 0 point, what this is saying is this linear point up to here is called the elastic region. The elastic region is you apply some load to the object and it goes back to where it started. Elastic bands are called elastic bands because you can have a huge amount of extension and it'll return back to the original point. So that's the elastic point. The yield strength is the point at which the object, it's typically a test section, or metal, carbon, whatever, it doesn't really apply to carbon, we'll come to that in a minute, it goes away from the elastic region. So you've applied so much force that it's now permanently deformed. And when you see forgings, that is what that means. So forged crank means sufficient force has been applied and it is now a permanently different shape. Then you have this sort of strain hardening, necking, and then fracture. This top point here is the ultimate tensile strength. So that is the maximum load that you can put in there. Strain has no units, it's just a percentage, so it's the extension over the original length. Stress is measured in pascals or pounds per square inch, and that is a unit of force per unit area. The only thing I haven't, necking is when you apply so much load that the area in between gets thin, and that's just a word that engineers use. And then fracture is the point at which it completely breaks. So this is a typical one for a metal, and you'll see this in textbooks all around. Now I'm showing you the one for carbon fibre. Carbon fibre is a bit different. So you've got the same thing here, tensile strength, tensile stress and strain, but it's a bit different. So carbon fibre, the fibre in it is extremely stiff. So this gradient here defines the stiffness. So this orange line is stiffer than the brown line. So if I go back to the previous slide, this, I should have really mentioned this, but the slope is called the Young's modulus, and it's the rise over the run, or stress over strain, and it defines how stiff the material is. For carbon, it is extremely stiff, but carbon fibre is made of two constituent components: the carbon, which is basically like string, and the resin, which is the bonding agent or the glue together to hold it all together, and that is comparatively weak. It's also not particularly stiff, because you can see this gradient of this curve in this area, so the elastic area is quite shallow. So if you combine the two together, you end up with this, which is the composite material, and that's why it's called composite, because it is a combination of two materials. Right, the results. The results. This is not a perfect test, so I had to get one of my mates to sort me out with this, and it's not a perfect test, so I'll be the first to admit that, but it gives you a good idea. Reverse engineering composite is extremely difficult. It's not like taking a metal sample and then testing that. The sample for a carbon, well, for anything, it looks like a dog bone, so you end up with this. It's actually more like that, so there's a gradient on there, and then it fractures through here. There will be some more bits and pieces on the website when I get round to it with the pictures and stuff like that. But basically, it's not a perfect test, because you're trying to use bits from a bike, whereas ideally you want a perfectly flat piece which is easy to mount and all of that kind of stuff. Cutting this causes some defects in there, so you have to kind of average it out. So there we go. If you got the takeaway from this before you watch the rest of it, is the Chinese carbon frame is basically the same as the Chinese carbon frame wearing the Western badge. You probably knew that anyway. And also, look at the relative values, not the absolute values. Right, this is the stress strain curve. So what we've got here is, if I get the pointer to work, got Trifox in blue, Canyon in orange, Cervelo, so that's my Cervelo, in grey, the Specialized in yellow, and I put it on here, a Canyon defect. So that is the Canyon frame. We took a defective piece out of it just to see what it was like. Now the obvious one in here is the, I should just explain, I did average a few of these out because I always took the strongest one. Anyway, what you can clearly see here is the Canyon has the stiffest carbon composite. It's clearly stiffer than the others, but it is not as strong. So the point of fracture is lower than, well, that's the Trifox, and that's the Specialized, and that one is the Cervelo. So the Canyon and the Cervelo are about the same strength, but the Canyon is stiffer. The other thing to note is how much a defect affects the strength and the stiffness. So something like a void, I mean, you've basically got no strength in it. There's nothing there at all. So yeah, bear that in mind. This is the E value of Young's modulus stiffness, however you want to call it. Now, Torreca Fibre, or Torre, is quoted at 240 GPa, gigapascals. Now, if you look at these, none of them are even close to that. Okay, and the reason for that is their quoted figure doesn't really include the resin. So the resin that you use has quite a big effect on the overall stiffness and strength of the frame. So Canyon is clearly using something compared to the other three, and bear in mind the other three bikes, apart from the Trifox, sorry, the other two, yeah, the Cervelo and the Specialized are fairly old. The Trifox isn't. That's like 6 months old, so it's, you know, of a modern design, let's call it. So there's a standard resin that it appears that these three companies are using, and the Canyon is using something else. So where's the loss? You know, because the Torreca Fibre is classed as 240 and the highest value we've got is 140, which is like half. Well, the layup, carbon fibre is, it should be an anisotropic there, but never mind. And there's some resin differences. So if I explain what the basic carbon construction is, so normally fibres run from, in one direction, in this case left to right, but it's like corrugated cardboard. It's only strong in one direction, so it's like a wood grain. So in this case, in this direction, the carbon is actually quite weak. In this direction, the carbon is extremely strong. So what they do is they lay up like a crisscross of layers to give you the strength and the stiffness. So now, and that's called a layup. So now it's strong in both those directions, so left to right and up and down, but it's not that strong in the 45-degree direction. So the next step would be to add a 45-degree layup. Right, you need to be aware that the material strength is not the be-all and end-all. Now, if you took a section of the Canyon and the Trifox frames, you can clearly see the Canyon varies its thickness. So I had to get a bit that was basically of uniform thickness. But you also need to be aware of the shape. So the Canyon shape maybe looks like that. The Trifox shape probably looks like that. Yeah, so the Trifox, I've drawn it exaggeratingly, but basically what I'm trying to say is the Trifox is beefier, so it has more material away from the neutral axes in both planes. The advantage of that is it is much stiffer, because a small increase, or you know, doubling the doubling the width increases the stiffness by 8 times, but you would have to, and you could achieve that, but you can't really achieve that just in strength of material. So that's the difference. So the Trifox, very, very beefy, the Canyon isn't. You know, the Trifox is, in my opinion, that is the way to go about designing a frame. Make it chunky, because you've got a bigger factor of safety in there. But the adverse effect is it increases weight. So, but it's not that much. So you know, a couple of 100 grams, 300 grams. You know, you might think is a lot, but you know, this cup of coffee weighs more than that. So there you go. Taking a dump weighs more than that. And you also need to be aware that build quality is key, because you've seen how much that defect has on the strength. You've basically got no localized strength in that area. So this is a close-up of the Canyon frame. Now I've put a green tick round there in the sense that don't worry about that. That's just movement in the layers from whatever they had inside, probably bag, has rippled the top layer, and in this case it didn't really matter. Of more concern are the reds. The reds are voids or defects that you'd class as reducing the strength. So just in the space of, well, what's my hand width? I don't know, 10 centimeters, something like that. So you're probably looking at 15, 20 centimeters. You've got 1, 2, 3, 4, 5 defects. I mean, they're varying in size. That one's a big one there. But there you go. So the takeaway is cheap carbon are just as strong or just as weak, depending on how you want to look at it. High second moment of area has more effect than high modulus carbon fibre. So you want structural strength in terms of geometry rather than material strength, which is the high modulus material. Smaller frames are significantly stiffer. If you reduce the distance between the points at which they are loaded, you gain a quartic relationship. A compromise exists between small sections, weight and stiffness. Frame designers are going to have to do this all day long, and a void has a severe impact on local stiffness. Build quality is way more important than the type of carbon fibre and resin. That is the end of this presentation. I seriously hope you enjoyed it. If you did, remember to whack the like button. If you didn't, go fuck yourself. And as always, keep banging your hairdresser.